Ever struggled with efficiently creating and managing meaningful descriptions for your tables and columns in your data warehouse? In this tutorial, we dive into a simple, automated, AI-based, and event-driven approach for precisely that. While we'll try to highlight cloud-agnostic concepts, this video will specifically be fashioning AI-created descriptions for tables and columns in BigQuery. We're going to use our trusted buddy, Cloud Functions, to make this happen. Specifically, an Eventarc-triggered function will be used for just-in-time updates to our BigQuery tables. Let's picture this. A BigQuery table creation leads to an Eventarc triggering audit log, which in turn triggers the Cloud function. This function then swoops in and updates the table metadata. To do this, the Cloud function needs to use an LLM via API. Specifically, we'll use the new Gemini model from Google Cloud and Vertex AI. Now that we've set the stage for our thrilling venture, let's buckle up and bring this vision to life. First stop, setting up that Cloud function. Here we are in our new project, heading over to the Cloud Functions neighborhood. We'll create a new function and give it a name. For our trigger type, we'll use the event-based, audit log-focused powers of Eventarc. Our desired BigQuery event type is in the Google sources. Specifically, we want the table-created event type. We'll trigger the function for any table creation in the whole project. There are a couple of role grants required. To move forward, we'll use the Compute Engine Service account if we leave this field blank. Experiencing some hiccups with the roles? Maybe it's because the Compute Engine service hasn't been activated. Let's nudge it awake and we should be good to carry on. Back to the drawing board, let's tweak our trigger and confirm if the grant goes through successfully. Everything's grooving, so we're moving. Just one more API to enable. Our weapon of choice today will be Python, but the same principles will apply if you opt for another language. This is just the beginning, folks. We're going to let the function loose first and check if it triggers successfully, all before we anchor it to any AI description creation. One key prerequisite left to address: our trigger focuses on Eventarc events plucked from the audit log. So, to ensure we actually trigger on these audit log events, we'll flick on the BigQuery audit logs. For completeness, we'll turn them on for all BigQuery services. After a successful deployment, let's forge ahead and now run a test with the BigQuery table. Being in a new project, our BigQuery is completely blank, no datasets or tables. So how about we craft a simple example table sporting a couple of fields? Let's swing back to our function to decode whether it's been successfully activated on that table creation. We'll get that answer using the logs. And voila! We notice that the event has indeed been triggered. There's the post 200 from Eventarc. We are presented with the event type, the subject, the API method, the resource name, and the principal. Feeling ambitious? Let's update our function with additional power, gleaning more information from these table creation events. Step 1. Let's bring the Google Cloud BigQuery library into our space using the requirements.txt file to do so. Over to importing that module in our code, it's time to use the module to squeeze out extra table details. Most crucially, we need the table schema. The associated function, getTableSchema, just needs the dataset ID and table ID. We now procure the column names and types revealed through our getTableSchema function. An obvious barrier, we will need to get the dataset ID and table IDs explicitly since our logs don't hold this information in the required format. No worries, we can glean this from our subject or resource name. Let's simply find the dataset's position in our resource name. Meanwhile, our table ID takes position number 5. With a successful deployment, we will craft another table to verify our progress. To maintain neatness and a clutter-free experiment, let's delete, then recreate the test table. Looking at our reliable Cloud Function logs, things are looking up. The dataset and table names slipped off the printer smoothly along with our columns. Next up, we'll get this function to call the AI API. Aiding in this big leap, we're heading to the Vertex AI Studio to experiment with Gemini and copy some example code. Aboard the Vertex AI train, we'll flip the switch on all recommended APIs to smoothen our ride. Once activated, we'll stroll over to the language portion of the Vertex AI Studio and play with the text prompt. We already have the Gemini Pro model coming in as the default here. For our first example prompt, we can use some generic names, but we're not giving the LLM much to work with for giving us meaningful responses. Let's look at another case with more realistic table and column naming. As we add more context, our descriptions start painting a clearer picture. Maybe you'll even want to pull sample data from the table or hard-code additional context into the prompt, but let's proceed along with this. We can grab generated code for easy integration into our Cloud function. Remember, we need to install the Google Cloud AI Platform module before running this new code in our function. Before rushing to parameterize our prompt and handle the table updates, we want to ensure our new code functions properly and has the required permissions to use Gemini. Now we can take this for a spin using our example description. Again, for this first run, we'll hardcode the prompt, testing things one small step at a time. Let's proceed to deployment, and if the stars align, we'll try another test with the fresh table. Just as promised, if we achieve a successful deployment, we'll create an example table once more. A quick peek into the logs and bingo, our printout looks promising. What's left now is to scoop this info into the table metadata. We can use the already imported BigQuery library to do this. We just need to introduce an update table operation. Since we're only getting a single output, a single reply from the Gemini Pro model, some simpler code here will suffice. Let's also knock down the max output tokens. We're aiming for sharp, concise descriptions here, up to 512 tokens or so max. Once our function is set to return that, we need to ensure that our main entry point handles the output. We'll also clean up our code a bit in other areas, including cleanup of some prints. Removing the superfluous, we'll get straight to the payload and use it to determine the schema before proceeding along. We want the table ID in our prompt, so let's bring this forward. To better use this logic, we should probably pull it out of the function. Before we get to column descriptions, let's fetch the table description. We'll also utilize the column list to structure the prompt. And naturally, we'll need to bring in the generate function for the actual description generation. Let's take a leap and deploy this function, shall we? In generating descriptions, it might be wise to have a table with more meaningful names. Maybe we'll follow the sales example from earlier. As is customary, let's use the Cloud Function logs to check our progress. Looks like we have an issue here. It's not keen on the lack of looping over responses. But really, that's an easy fix. Let's try a simpler path and accumulate all responses into a list, and then return the first response text. We're sort of negating the streamlining approach established earlier, but that's okay. To make recreating tables easier, copy the schema as JSON from the existing table before deleting it. Create a new table with that schema pasted in, Then we should be able to retest our function here. We have a couple of things to fine-tune now. First, we need to increase the memory of our function, which is a pretty small value right now. Then we've got a variable issue with the table variable. Both of these can be remedied in an edit operation. Let's bump up to maybe a gig of memory in a single CPU. In the code, let's see if we have our table variable, and indeed, we don't actually have that. We need to extract this variable out of the function, so we might go ahead and remove this whole thing, pulling it into the main entry point. So if we bring that down here, we'll initialize the client, get the table ref and the table, and then do our work. So now we have this table object and should be able to do things down here like setting the table description and schema before actually updating the table on the server side. Again, for this next test, we will use the hack of copying the JSON schema to save some time. All right, we still have an error here. It's not liking our use of the dataset ID variable, but that's a super quick fix. Let's move the dataset and table ID up near the top, and we'll of course need to move the payload work there as well. Let's repeat that testing process from before to see if this worked for us. We have a successful function execution, which is a really good sign for our description generation. And if we look at the table, everything's looking great. We have descriptions for the customer, quantity, price, e-commerce field, and pay field. Note that it's using table, schema, and type context to infer details for use in description generation. We'll provide the code for this tutorial in the description of the video, along with this diagram file. Thank you very much for watching, and please enjoy responsibly.